This video tutorial is to describe how to process event mode data using the SANS reduction package. To get started, simply select Event Mode Processing from the Macros menu. This will automatically load the normal SANS reduction package along with the event mode processing. Event mode data is neutron scattering data that's collected in a special mode where every neutron event is recorded with its XY position on the detector and its arrival time. This results in a binary stream of events where each event is encoded in a 32-bit binary word. Data in this format are essential for techniques such as Tizane, time of flight, any sort of time-sliced or kinetic data. And this package allows processing of this event stream into any number of time bins spaced as needed for the experimental conditions, and finally exporting the data as if they were individual VAX data files. In general, there's two kinds of event data: either oscillatory data, where data is collected for a certain period of time, and then a reset or a T0 signal is sent, resetting the clock to 0, and then the process is repeated. In this way, data can be accumulated over many repeated cycles of some sort of environmental condition, and then these can be collapsed and collected into larger data files with better statistics. The second general type of mode is stream or continuous mode, where data is simply collected as a normal data file with a start time and a stop time, and then this longer data file can then be sliced up as needed. This is in general useful for much longer or slower kinetics. But both of these are useful and can be very helpful to understand what is happening in a process. So the first thing that needs to be done is to say where the data is, and this is done as usual from the SANS reduction controls by picking the path. I have some example data sets here. We'll start with some oscillatory data, so I'll choose that folder. And then we can load a log file. And this is typically a data file that starts with an event. It's tagged with a date and time string starting with the year. Unfortunately, this number has absolutely nothing to do with the file name. It is closely related to the actual collection time of the VAX file, although the clock on the histogramming memory and the clock on the VAX are not in sync. If we select this .hst file, we can see these files are generally much larger than you're used to dealing with SANS data files. SANS data files are typically 33 kilobytes in size. These event streams can be tens or hundreds of megabytes, even approaching gigabyte sizes. This requires some special processing, which will be detailed in a separate video. If we click Open, this will load in the data file, and in this mode of loading it in, we have a tick box selected here to remove bad events. This will do its very best to remove any sort of misencoded binary points and any sort of spurious events that have ended up in the event stream. It will not catch them all, but it will do a pretty good job at getting rid of them. If it doesn't get rid of them, this will be discussed again in a separate video where the events can be adjusted to take care of these events that do not belong. What shows up is two windows, one showing only the first 1,500 events. In fact, there were 1.3 million events, or essentially neutron counts, loaded with this data set. Some fraction were actually removed because they were bad. In this case, a small fraction. If this number gets to be very, very large, then you'll need to take a closer look at your data file, considering there's something probably wrong. This is oscillatory data. You can see the time goes from about 0 up to about 0.6 seconds, and there's a pretty quick reset from event numbers here. In red, the plot here, this is the differential of the time, event arrival time. This is really for diagnostics to be sure that there's not any odd skips, jumps, or spurious events in the data file. If this is just simply a noisy looking oscillating result, that's good. That's what it's supposed to look like, because that represents basically the jitter in arrival time of the events. So, given that this data is good, looks good to me, if you wanted to see all of the data, this would take a bit of time. The way to do that is Control A, which essentially says select all, and this will show the entire data set. You'll get a little watch or spinning beach ball or hourglass or something as it takes the time to actually display these 1.3 million data points. Packs them all on there. It's not terribly instructive. There are other better ways of viewing this. I can close these for now. I don't need to see them anymore. Once this event file is loaded in, the next thing I'd want to do is actually decide how many slices I want to bin this in. The maximum time is 0.6 seconds. I can either use equal bin spacing, that will be equal time width, a Fibonacci bin, which will be sort of increasing length of time as you go farther on, or custom bins. And again, this will be discussed later. If I click bin event data, this will go through and take all of those 1.3 million events and bin them into 10 bin widths of equal time. And if I show the bin details, I can see two things. I see the 10 bins and the number of counts in each bin as a bar graph as a function of time, and as well the bin count, the bin end time, and the bin width. The bin widths here are equal, of course, for each bin because that's what we set. And we can see there is an oscillating feature to the number of counts as a function of time. We can also see this in the data. We can see not the oscillating number of counts, but we can see a change. As we scroll through the slices, we can see a change in the actual scattering. The inner ring here we see flips its orientation. Since this data is good, we don't need to do any of the editing or splitting of large files. We can actually simply, we now want to take these 10 data slices and export them as VAX files so that we can then reduce them as if they were actually normal files. So if we click on Export Slices, it wants to know basically a first fake run number, and it'll number these then 1 through 10, and then a 5-character prefix, again, as if you were writing out a VAX file. This is fine. I say continue, and it says, is the full data file loaded as a raw data file? If not, load it and start over. What it's asking for then is the actual raw data file, the VAX file, that was collected at the same time as the event file. And the acquisition system is set up to do this. It's needed because when it writes out the fake VAX file, it needs to know all the header information of how the instrument was set up, and it also needs to know things like how many total monitor counts were collected and how many total detector counts were collected. So then it can divvy up those monitor counts and detector counts when it exports the slices, of course in proportion to how you have the binning set up. So if we display the raw data file, and it's in fact this May file, this is what the total data file looked like, which is very different than what it looked like as a function of time. So once that's actually loaded in, we can now go back to this, say export slices as VAX. They'll number them sample 001 and on. Yes, it's loaded in. I didn't save the path. I need to actually save the experiment so it knows where to put it. And we're going to put this in the same oscillatory folder. Now, everything's happy. It exports the files. We can now go to the desktop and see that it's saved 10 data files from 1 to 10. If you were to go and now get a file catalog, the original data file is there, and this was collected for 14,400 seconds. I split it into 10 different files, getting 1,440 seconds per file. The counts now are split up. Total counts of 1.3 million counts are now split up to approximately 130,000 counts per file. You can see the counts do vary as expected. The count rate varies as expected. And now these files can be processed as normal as if you collected these files during a normal SANS experiment.